Differentiation video 6, a little extra look at increasing and decreasing functions. If we were asked, for example, what's happening to f of x equals 5x to the power of 4 plus x to the power of 5 when x equals negative 2. We know how to deal with that. We say, well, let's differentiate if we're asked whether it's increasing or decreasing, because that's rate of change. 20x to the power of 3 plus 5x to the power of 4 is my general rule. We want to find out increasing or decreasing when x is negative 2, so I'll substitute negative 2 into my second equation. First equation is points, second one is gradients, which is rate of change. 20 lots of negative 2 cubed plus 5 lots of negative 2 to the power of 4. That's 20 times negative 8, negative 160, plus 5 lots of 16, that's 80, which would give me my f dashed negative 2 is negative 80. And because it's negative, we say, oh, all right, because f dashed negative 2 is less than 0, i.e. negative, therefore, at that point, the function is decreasing. And that's straightforward enough, I hope. But a trickier question that they sometimes ask in the exam is, show that, for example, f of x equals x cubed minus 3x squared plus 3x negative 10 is never decreasing. Or perhaps an example is never increasing, or is always decreasing, or something to that effect. Well, we can use what we did with stationary points before. We could say, well, I'll take my function, I'll look for stationary points, so I will differentiate. Then for stationary points, the gradient is 0, so I'll set my derivative equal to 0. Factorize, first look for a common factor. So that's 3 lots of x squared minus 2x plus 1 equals 0. Divide both sides by 3. I can still factorize what's in the bracket. So that would be 3 lots of x take away 1, x take away 1 equals 0. We always remember to write in the equals 0. Oh, two things multiply to be 0. The 3 is not 0, so x take away 1 equals 0. And the second bracket's the same, so I don't need to write it again. So x equals 1. I have one stationary point. Now, we're not asked for the y-coordinate, so I don't need to work out f of 1 to calculate what the y-coordinate is. All right, but I can do a nature table to look at increasing and decreasing. And so I say there is my x value of 1. I'm going to be looking at my gradient here. I'll use f dashed x because that's what was in the question. We're talking about functions. And we'll look at the slope of the line. And I can take my number 1, value of 1, plug it back into my derivative up here. See, is that positive or negative or 0? And of course, when I put it in, I get 0, which is what I expected, because that's what I was solving for, derivative equal to 0. So this bit's horizontal, and I can say what happens before 1. I'll just say x is 0 up here, substitute in here. Oh, I get positive. And what's happening when I go past 1? So let's say I'll put in 10, and I work out this. 3 times 10 squared minus 60 plus 3. Okay, that's positive again. And then say from my nature table, okay, can say f dashed x. All right. Now I can't say it's always increasing because at this point, even though it's only for an instant, the function is not increasing, but I can say f dashed x, all right, is greater than or equal to 0 for all x. So it can be 0, but it's definitely never negative. All right, therefore, if it's never negative, we can say the function itself is never decreasing, which is what the question asked me to show. And that's fine. It assumes, of course, that when we're doing the derivative and looking for stationary points, that we can find that there are stationary points and it equals 0. It is possible to have a function that when you differentiate it, there are no stationary points. Or we could also say, well, this is actually quite a long process, doing the nature table and working it all the way through. There is a much quicker way that works, and especially if sometimes there are no stationary points, so we can't set equal to 0. So this way will work 9 times out of 10, and it's perfectly valid 9 times out of 10. If we can find stationary points, then this is a valid way to say the function is never decreasing. But what is much quicker is, if I go back to the original question here, is to say, let's find the derivative. F dash x, 3x squared minus 6x plus 3. Factorize, and as you're factorizing, we're going to be, because of the question, we're going to be saying, well, if it's never decreasing, or indeed never increasing, we're going to be looking to get something squared. All right, I'll explain why in a moment. So I'll take out my common factor first, just as we did before. Here's something squared, so my f dashed x is 3 lots of x minus 1, which is something squared, as I say. So take the common factor out first, because otherwise this would not be obvious that we had a squared term in here. X minus 1 squared. And we know that anything squared, the smallest value is 0. Right? We can't say it's always positive, because if x is 1, we'd have 1 minus 1 is 0. 0 squared is 0, which is not positive. But it certainly cannot be negative. So from this point, we can say, oh, because I look at this, and I can say this is just a positive number times something squared, we can say immediately f dashed x is greater than or equal to 0 for all x. Therefore, the function cannot be, it's never decreasing, just like our conclusion over here, but it was much shorter. So to recap, we simply differentiate, factorize, take out the common factor first, if there is one, we always look for that, but what we have remaining should go into something squared. And because we know that something squared cannot be negative, then that does that. If the common factor if we look at the x squared term, if this was a negative term here, if this had been negative 3x squared, I'd have taken negative 3 out as my common factor, and then negative 3 times something squared, which cannot be negative, so negative 3 times 0, or negative 3 times something positive. Then I'd say, oh, my gradient is always less than or equal to 0. Therefore, the function is never increasing. But it all depends on the factor in front of my x squared term here. Take out a common factor, and then when you factorize the remainder, we should have something squared. Makes this much quicker. And that's it.